sing along.
Okay. Hello, everyone. How's everyone doing? Yeah? It's good to see you all. Thank you for those folks that are putting their camera on. I appreciate that. It's nice to see your faces. I miss you all very much, even though some of you I have never met, but still, for some reason. Okay, any announcement? I can.
The solutions for homework 1 were posted, and you have to self-grade your homework as part of homework 2. So there's also a rubric that was posted. They're all on the course websites.
Yeah, be very critical of how you self-grade. There are going to be some spot checking. So.
Yeah.
Anything else?
I think that's all.
Okay.
So
Homework 2 has some either MATLAB or Python programming, and so you can actually choose which one you like. Just so I get an idea of what's going on in this class. Raise your digital hand if you prefer Python. So it's kind of split, I guess, half. Okay, raise your digital hand if you prefer MATLAB. Okay. All right. So yeah, it should be a fun exercise. It's an exercise with 2D Fourier transforms, jinks and sinks and rect and pillboxes and oh, you want to do yeah, Lee, you can do C++. Yeah, go for it. No problem. Yeah. Hardcore. Absolutely. All right. So where were we last time? Last time we derived a little bit hand wavy, but not so much. Derived the Fourier relationship of a one-dimensional readout when we have a gradient on. So let's just go back to the setup. This is the setup. We have a gradient on, and our object was a rect. We turned the gradient on, so we have a field distribution of W0 plus gamma GX times X. And if we actually look at a piece of magnetization, let's say a magnetization over here, that magnetization will resonate or will produce a signal that is proportional to the size of the magnetization at that position. And then it will produce a frequency, and the frequency will be proportional to the field. Hence, it's going to be e to the minus I omega 0 plus gamma gx x times t. So this will be the signal that comes from this small piece of magnetization. And then if I move to a different x, then the only thing that is going to change is here. So that will change some constant here, but then effectively it will be the same. So if you look at now a signal picked up from the entire volume, remember that we pick up the signal using inductive coupling to a coil. And if the coil has uniform sensitivity throughout the volume, then it's effectively integrating the signal from the entire volume. And so we have an integral over x of m of x e to the minus I omega 0 plus gamma gxx times t. If you stare at this long enough, you kind of realize, you know, it kind of looks like a Fourier transform. It's not exactly a Fourier transform because It has a t here, and we're interested in spatial frequencies, not in time. It also has this constant, like minus I omega 0 times t. So, but overall, it kind of looks interesting. And so we can massage this one to look like a Fourier transform. And what we've done is we took the part that's kind of constant, that doesn't depend on x, outside of the integral. So this is the part that doesn't depend on x. And this is just a constant modulation. Well, it's not constant, but it's just a modulation component e minus I omega 0 t, but it's independent of x. Okay. And then the other thing is we made the integral here, like whatever is in the exponent here, to look like a kx. Like if this was actually a kx times x, that would be a Fourier transform, right? Like if we had e to the minus I 2 pi kx times x, that would have been a Fourier kernel. This is not a Fourier kernel, but what we're going to do is we're going to multiply by 2 pi, divide by 2 pi, and then call this kx. So we're going to call gamma over 2 pi gx times t, we're going to call kx. Okay, so kx is a function of t, and it's defined as gamma over 2 pi gx times x. So now this looks like now a Fourier transform. This is exactly a Fourier transform with kx being the variable. Okay, with kx being the spatial frequency. And this is some component that we have up front. So effectively, if you realize what it is, this is a Fourier transform evaluated at a frequency which is kx. Okay? At a frequency which is kx. That's the Fourier transform evaluated at that. Okay, so the whole signal is now going to be proportional to e to the minus I omega 0 t. And then the Fourier transform, the one-dimensional Fourier transform of mx, and then evaluated at some kx. Now, which kx? Well, that depends on the time. If we look at what is kx for t equals 0, well, then kx will be equal 0. And as time increases, we are actually getting higher and higher spatial frequencies, right? Because as t increases, then the whole value here is going to increase, because this is just constant. So as this increases, the whole thing increases, and so kx will increase. That means that as time goes by, we are reading information about mx in the frequency domain at increasing spatial frequencies. Subtle, maybe, but try to digest that. Okay. Again, the signal that we get is as if we computed the Fourier transform and evaluated that Fourier transform at particular kx. Which kx? Well, that depends on our time signal. In the beginning, we're going to collect at k equals 0. And as time increases, we're collecting higher and higher spatial frequencies. So effectively, we are moving in the spatial frequency domain of the object and collecting samples. That's what we're doing. All right. So we're moving in the frequency domain at this speed, gamma over 2 pi gx times t. If gx is large, we're moving faster. If gx is small, we're moving slower in the frequency domain. Any questions? Try to digest that. Okay, so it's all about a Fourier transform. So if m of x is some rect, then the Fourier transform of f of m of x is a sinc. Okay, that means that the signal that we're going to pick up is going to be a sinc evaluated where? Well, at time t equals 0, it will be evaluated at 0. And then as t increases, then we start evaluating at higher and higher frequencies. So this is t, but is also corresponding to k of t, right? Because these are linear functions of each other. Okay, there's just a scaling between those two. And so this is the modulated version that is multiplied by that. But if I demodulate by this factor, then I would actually get the envelope, and the envelope of that signal is going to look like a sink. Okay, and so I'm going to collect data for a certain amount of time, and then I'm going to stop. So this is the data that I've collected for an object that was erect. If I apply a gradient in X and I excite and collect data, the data that I'm going to receive from my analog to digital converter is going to look like a sink that's going to start at 0, like half a sink effectively, and then I'm going to stop at a certain time and stop collecting data. Does that make sense? Now, if this is the data that I collected, if I want to reconstruct the image, what is m of x, I could have taken a Fourier transform of this. And taking a Fourier transform of this will give me a real part and an imaginary part, but let's just stare at the real part for a second. And you'll see that, in fact, the real part is erect, and it looks like the image. The fact that I collected only half of that sink has an effect, and that effect is going to be a large, imaginary component. So if I look at the magnitude of this, the magnitude of this is going to look more like something that is blurred, right? So the magnitude is going to be looking like it's blurred. However, we're going to later see how we can actually complete the other part of that sink somehow. Okay, but you can kind of see that it's almost a one-dimensional projection. So computing a Fourier transform of the time signal that we collected from the MR system, a one-dimensional Fourier transform is effectively like a projection through a two-dimensional object, or if it wasn't a one-dimensional object, that will give me the object. Okay? Are we all good? Raise your digital hand if we can continue. This is critical. Or ask a question if it's unclear.
One quick question. About the actual signal we are going to receive is a carrier or the baseband. What kind of shape we're going to see?
So this is the signal that is received by the I guess the antenna, by the coil, right?
Yep.
And then the receiver is pretty much a radio, and a radio performs this demodulation in hardware. And then the baseband signal is sampled using an analog to digital converter.
So the demodulation is done by the machine.
Yes, the demodulation is done by. Yeah, because the scanner knows what the resonance frequency is, so you can just demodulate by that. And it's going to be 127 megahertz, 127.69 or something like this megahertz at 3T.
Got it. Thanks.
Okay. Yeah, that's
a
good
question
point.
as well.
Thank you.
Actually,
yeah.
So in general, if m of x is real, then won't its Fourier transform have symmetry that we can just sort of use to reflect the signal over, and then when we take the inverse transform, we just don't have like the extra component in the imaginary part?
You know, I mean, you're absolutely right. If m of x was real, then its Fourier transform would have a conjugate symmetry. That means that knowing half of that signal, I know everything I want to know about the other part, right? So then computing a Fourier transform, taking the real part is exactly the same operation.
Okay, that makes sense.
And so then you could see that the real part is actually the image.
I see.
But, and this is called also half Fourier imaging. Like it is actually done in practice in some cases. But in fact, there's always some phase on the object. And so that is not completely true. And so there are subtleties about how to go about reconstruction. So often you really want to also capture the other side somehow, because it's not going to be perfectly conjugate symmetric.
Gotcha.
Like everything I said in MR, it's same, but different. You know, there's always some subtlety. But yeah, but in principle, you only need half. In practice, you need more than half. Okay. Very nice questions today. Thank you. Okay. So how do we get an image? All right. How do we get an image? So there are several key components. One is that we're going to excite the volume, but instead of exciting the entire volume, we're going to only excite a single slice within the volume, okay? What's called a slice selective excitation. I kind of demonstrated before when I have hand waved with the piano and the tuning forks, how a selective excitation can be done, right? You apply a gradient and then you apply an RF pulse at the right frequency such that it only excites the spins that, only excite particular sets of spins that are on resonance, because anything else because of the gradient will actually resonate at a different frequency. So we're gonna excite a slice, and the reason for it, this is kind of like a dimensionality reduction. If I excite a two-dimensional slice, then I only need to encode the spatial position in 2 dimensions rather in 3 dimensions. Because the slice is thin, then I don't care about, I don't need to resolve what's within the slice, across the slice, the through slice. I don't care. It's really what is the 2-dimensional distribution. So it saves me a lot in terms of the amount of encoding that I need to do in order to get an image, right? If I could potentially, let's say, just selectively excite a single pixel, well, then I don't need to do any encoding whatsoever, right? Because the signal that I'm going to get is going to be from this one pixel. And then I can go and excite a different pixel, and then I can go excite a different pixel, and so on and so forth. But you can kind of see how it could be very tedious and long to do that. An alternative, I can maybe excite a pencil beam, like just like a one-dimensional, part of the volume. If I only excite that, then I need to encode just one dimension. But that is also pretty difficult. The easiest way of doing things is actually exciting a slice, because that only requires you to apply a gradient and then RF at a particular frequency, and then you excite a slice, and then you end up only need to encode 2 dimensions out of 3. Okay, so that is a key component, selective excitation. That is a Nobel Prize kind of idea by Peter Mansfield. All right, so then I need to do some spatial encoding. Spatial encoding, there's actually 2 forms of it. One is frequency and one is phase encoding. And more on that later, okay? So we'll separate these spatial encodings into a frequency dimension and phase encoding dimension. Just bear with me with that, right? I'm just introducing the notion of phase encode and frequency encode right now. We'll talk more about what they mean, okay? So we'll do some spatial encoding. So excite, encode, and receive the signal. Then our signal is going to decay, and then the magnetization afterward is going to recover. And so what we're going to do after that happens, we're going to excite again, do a spatial encode, wait till the signal decays and magnetization recovers, and then repeat that n times. Okay, this is pretty much the sequence of events. And then after we collected enough data, we're going to perform some image reconstruction to take that data and make an image out of it. And it's probably going to have a Fourier transform in that operation somehow. All right. Are you ready? Dun, 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 dun. Did you like also 31p? It's a pretty good song, huh? Nucleus ILF best is 31p. All right. So here's the idea about non-selective excitation. So we talked about like briefly about selective, but what is non-selective? Effectively, what you do is you apply some RF that is just a pulse. If you apply this pulse, then all the spins in the volume resonate at exactly the same frequency, and that pulse that you're going to apply is going to be at that frequency. And so it's going to effectively excite all the magnetization throughout the entire volume. And then the signal that we're going to get is going to be an integral over the 3D space. Okay, so the signal that we're getting is over 3D space. So that would require us to perform spatial encoding in X and Y and Z. So applying X and Y and Z gradients in order to do that. We'll talk about that, but we'll get to that more later when we talk about chapter 5. Now, what is selective excitation? Well, selective excitation is you apply an RF that has a limited bandwidth, okay? So it has a certain bandwidth. And so if I apply a sync pulse, okay, a sync pulse, while having the gradient on, then if the gradient is on, that means that spins over here, they're not seeing, they're outside of the bandwidth of the RF, so they're not interacting with the RF. Spins down here are also outside of the bandwidth of the RF, so they don't interact. But only spins within the bandwidth are going to be excited. So now I have this slice excited. The signal that I'm going to get is the integral over the entire volume, but the only spins that are excited are from that slice. So I really don't need to encode this dimension because this dimension is very thin. The only dimensions that I need to encode is this dimension and its orthogonal dimension, X and Y. But the Z direction, this dimension, I don't need to encode because I encoded it by selective excitation. Does that make sense? It's like, the example would be, let's say I'm talking to this class and I can ask you a question and all of you would answer at the same time, right? Then I would kind of have a hard time trying to figure out kind of which one of you is actually speaking and what you're saying because everything kind of overlaps. But what if I somehow just select one of the columns, right? So I have a few of you speaking at the same time. So maybe there's a way for me to easily try to separate between your voices because there's just less of them. Does that make sense? Okay. Now, when I apply the gradient for excitation, I apply the gradient during the RF, and then for some reason, there's something I need to do. I need to apply a gradient in the opposite direction that is exactly half the area of what I excited. This part here is a mystery that without it, nothing would work. And more on that soon. But yeah, that's a mystery right now. Again, some of the subtleties of MRI. Without this part, nothing works. If you add this, you get an image. With this, and without this, you don't get an image. But we'll get to that. Okay. Just want to kind of stimulate your curiosity. What is this thing? Okay, so if I want to excite a slice, what I'm going to do is I have a volume. Okay, I'm applying a gradient. Okay, so my resonance frequency varies within this volume. Okay, my resonance frequency varies within this volume. And I have a coil here that is inductively coupled to this entire volume. Now, because I'm applying a gradient, then there's a resonance frequency variation from down here, low frequency, all the way to high frequency. So if I apply, so there's kind of a mapping between position and the resonance frequency, right? Gradients, this is if I apply a gradient, some gamma over 2 pi gz times z, that is the frequency. That is the mapping between the gradient that I'm applying and frequency. So if I want to know, for example, what frequency is here, so I'm going to go, and that's the frequency corresponding to this position. If I want to know what is the frequency at this position, well, I'm just going to go here, and it's lower frequency. And here, it's higher frequency. And here, it's even higher frequency. Okay? If I apply stronger gradient, basically all that means that the slope is going to be more steep. And so now the mapping is going to be different, right? Like all, everything will, kind of like, yeah, the mapping will be different. So effectively, if let's say I apply a stronger gradient, then this place over here would map to here, and this one would map to here, right? So it would be much more narrow. Does that make sense? Okay. All right. So in order to, if now I have mapping between space and frequency, that means that if I want to excite that slice, I need to apply energy in a certain range of frequencies. So the Fourier transform of my excitation field needs to have this form at those frequencies, because that means that then it will interact with this part of the volume. Okay, so the Fourier transform of my excitation field needs to look like a rect, such that I'm going to excite a perfect slice. Now, what pulse, what type of B1 field or B1 of T would have a Fourier transform which is a rect?
Sinc.
I'll give you 8 points for that out of 12. And the reason I only gave you 8 points is because, yes, the envelope is a sinc, but it also needs to be modulated by some center frequency, right? It needs to be a sinc that is modulated by a center frequency around a certain, bias, right? Because if I just do a sinc, then everything will be around 0.
Yeah.
So it's a modulated sinc. Okay. All right. So here's the excitation field. It's pretty much, I have a carrier frequency, that is the center of the slice, E minus J omega 0t, or E minus I omega 0t. That is the center frequency. And this is the envelope shape of the slice. So this is pretty much will be a sinc. So here is the B1 field, which is a sinc, multiplied by this modulation. Okay. So the slice profile is approximately the Fourier transform of the RF envelope. Right now, I'm waving my hands and telling you, yeah, it needs to be a Fourier transform. But you know what? Like everything in MR, it depends. And it's just going to be approximately. And we'll get to that, what it means, why is approximate, and so on and so forth. Because there is some nonlinearity there that happens. Okay, we'll get to that. Okay, but it is approximately the Fourier transform of that RF envelope. Okay, so just remember that is similar, so it's going to look like a sinc, but actually it's not going to be perfectly a sinc. It's going to be something slightly different, depending on how much flip angle you're going to want to do. Okay, so the Fourier transform of this B1 field is a rect of f over a. A is the width of the slide, so we need to choose an RF pulse to do that, and the RF pulse B1 should be something like a sinc, okay, approximately a sinc. Okay, so here's how we draw the RF excitation. This is a pulse sequence diagram where this is time, and this is the RF waveform. This is the gradient in the z direction waveform, and we tell the scanner, at this time point, turn on the gradient in z, keep it on for a certain amount, and then make it negative, keep it negative for a certain amount, and then turn it off. Okay. While the gradient is being positive, turn on the RF, and trace a modulated sync RF pulse. Okay, that's what the scanner hardware is going to do. It's going to feed RF into the RF coil, is going to feed a constant current into the gradient coil, and then here a negative current into the gradient coil. Does that make sense? Just from a, now, why is that? I'm going to keep it a secret right now. You know, why we need this? I told you, like, you need it. Without it, nothing's going to happen. But we're not going to talk about now why. I'm just going to keep it such that you're curious. And so we're going to talk later what we need that. So effectively, after performing this, if I look at the distribution of the magnitude of MXY, the magnitude of the transverse component of the magnetization as a function of Z is going to look something like that. Okay, so I'm going to be exciting something that, you know, in the Z direction would look like a slice. Okay, if the gradient is stronger and I'm applying exactly the same RF pulse, then my slice will be thinner. Right? Why? Why will be thinner? So exactly the same bandwidth, but now I'm applying a stronger gradient. Right?
Because the range of frequencies is more narrow?
The range of frequency through the entire volume now is wider, so across that particular range of frequency, it represents actually a narrower, a smaller part of space. Right? The same volume now covers a larger bandwidth, so the same bandwidth represents a smaller space. So this is, for example, a way to control the slice thickness, is changing the gradient amplitude. This is how you control the slice thickness. All right.
Professor, quick question.
So here's a quit. Oh yeah.
So in the previous slide, you had MXY. What are those all the same just because like in the XY plane, they're all excited the same amount? Like what? Yeah.
Yeah, so MXY is a transverse component, and I'm looking at the magnitude across the transverse component. So it's MX plus MX square plus MY square root. Yeah, that's kind of what I'm looking at. Now, if I apply an RF pulse, you know, it could be that everything is in the MX direction, but it could be there are some components in the MY direction too. But when I look at the magnitude will look like this. Actually, the magnitude would look like this no matter if I have this or not. What would happen actually when I add this thing, that would move all the magnetization to be in MX or MY, but not both. So we'll get to that. Okay, so, but yeah. But effectively, we're looking at the transverse magnetization magnitude, right? We had magnetization in the longitudinal direction, and by performing an RF excitation, now everything goes into the transverse plane. The transverse plane is MXY, okay? Whether it goes to X or Y, well, that depends. But the overall magnitude is going to look like a sink, okay? So here's a quiz. Let's do it together. My B1 field is e to the minus I omega 0 t, sync 5,000 times t. Okay. Hold on for a second. Yep. 5,000 times t. Okay. And my gradient, GZ, is 1 Gauss per centimeter. So my question is, what is the slice thickness that I'm going to be exciting? How do I go about it? What does GZ does? What does it map?
It maps
What is
locations to frequencies, resonant frequencies.
That's right. Yes, it maps position to frequency, right? Okay. So GZ maps position to frequency. Now, what does the sync pulse does? The sync pulse has certain range of frequencies where it has energy in, right? So first, if I figure out what is the bandwidth, like how wide, I mean, it's going to be a rect, right? Like the Fourier transform, if this is a rect, I need to figure out how wide that rect is in frequency. If I know how wide is it in a frequency, then by looking at GZ, I can map frequency to position and figure out like how this bandwidth corresponds to slice thickness. Does that make sense? So if we go through this exercise, the Fourier transform of B1 of t is, do we care about, does this matter for the slice thickness? What is this component determines?
What are you pointing at?
Oh, you don't see?
Yeah, I don't think
What?
we saw.
Can you see
Okay,
now?
now, yeah.
Huh, weird. Okay, so can you see now? So what does this component contribute to?
The carrier.
Yeah, but what the carrier does. If I change, let's say, the carrier frequency, what's it going to do to the slice?
It'll shift the slice.
It will shift the slice in Z, right? In the Z direction. It will not affect the width of it, but it will definitely shift it up or down. All right. So this shifts the slice up or down. This affects the width. So the Fourier transform of that is actually proportional to rect of what? F over 5,000. Okay. So that means that if you actually look at the Fourier transform, then the Fourier transform is a rect that goes from F0 minus 2500 hertz to F0 plus 2500 hertz.
Wait, Mickey, now the
Okay.
screen is cut a little bit. We can only see half of your screen. Okay,
And now?
now it's good.
Okay. All right.
You just turned on
Okay,
the conjugate symmetry function.
Yeah, that's right. Okay, so now what I need to figure out is I need to figure out kind of what is this mapping of GZ, right? So I know that gamma over 2 pi times GZ corresponds to 4257 hertz per centimeter, right? So gamma over 2 pi GZ correspond to 4257 hertz per centimeter, just by definition for hydrogen. So if I know that gamma over 2 pi GZ times delta Z, which is the slice thickness, I know that corresponds to 5,000 hertz, right? So I multiply by centimeters, so I get hertz, right? If this is hertz per centimeter, I multiply by centimeters, I get the units hertz. Okay, well now I can then find what is delta Z. Delta Z is about 1.17 centimeter, right? It's 5,000 divided by 4,257. Okay, so applying this type of a pulse with this gradient will give me a slice thickness of 1.17 centimeters. Right, so this is kind of the types of exercises when you design an RF pulse that you have to go through in order to physically, like when you prescribe on the scanner slice thickness 3 millimeters, there's these calculations of, how much you need to stretch the sink and what is the gradient amplitude such that the actually slice ends up being the right size from a sequence point of view. Oh, and here's with a nicer handwriting. Okay. All right. So back to spatial encoding. Okay. So again, there's this part which performs the excitation. After I excite the magnetization, right, I'm going to now, let's say now I have an object that is pretty much a box object. So it is uniform amplitude across a box covering X and Y, right? So this is kind of like our image. And if I apply then an RF pulse, I excite a slice. So I excited this magnetization, right? Because this is in Z, right? And this is only XY. So now I don't have the Z direction anymore. Now I only care about X and Y. Now I apply an X gradient. If I apply an X gradient, if you remember, the signal that I'm going to get is the integral of the magnetization, the integral over space of the magnetization multiplied by e to the minus 2 pi kxx plus kyy. Okay. Now remember that kx is gamma over 2 pi gxt. So effectively, if I apply an X gradient, if this is the two-dimensional Fourier transform of the object, that signal, the one-dimensional signal that's going to look like a half a sink, is pretty much the evaluation of the two-dimensional Fourier transform along this particular line. So it's like when I apply a gradient in X, I'm going to travel in the two-dimensional Fourier transform of that image and collect samples till I stop. Okay? This is effectively what's happening. Now, why is it half a sink? Well, because the Fourier transform, the two-dimensional Fourier transform of this rect is actually sink in X multiplied by sink in Y. Okay, so this is why it's a sink in this direction, or half a sink, right? Because we start here. Now, in order to get a full image, somehow we need two-dimensional encoding in order to cover it. Otherwise, we don't have information of the entire Fourier transform. We only have kind of one line, right, in the frequency domain. But we need to cover the two-dimensional Fourier transform in order to be able to recover it. Okay? So if you actually think about it, this line over here in the frequency domain is kind of like a projection. So it's like the Fourier transform of the projection. So if you know the center slice theorem, the center slice theorem says the following. If I have some slice, some object, mxy, and if I compute a line integral through this object, so I basically integrate in a particular direction on this object, okay? I perform an integral. If I perform an integral along line integrals, I will get a one-dimensional projection of this object, right? This is the one-dimensional projection of this object, because here it's the thickest, so the object is thickest here. Here it's the thinnest, so it's going to be thin. Here it's also thin, so it's going to be thin. Okay, so computing this projection. Okay, so on one hand I have an object here. On the other hand, I have the two-dimensional Fourier transform of this object. This is this shape or whatever it is. Okay, now if I computed this projection, so this is the projection, and I took this projection and I would have computed a one-dimensional Fourier transform of that projection, the central section theorem says that the 1D, one-dimensional Fourier transform of this projection, f theta of x, is actually a line through the two-dimensional Fourier transform of this object. So making a projection along this axis, it's the same as evaluating a one-dimensional line on the 2D Fourier transform. If I then performed, let's say, a projection in this direction, then that would give me a line, this line in the Fourier transform. And then if I would have performed, let's say, projections in this direction, then that would give me a line in this Fourier transform. Okay? So projections effectively give me, there is a relationship between cross sections of the two-dimensional Fourier transform and projections. Now, if you remember from CT, remember that we talked about CT? I showed you that it is possible by computing projections from different directions to reconstruct the object. I don't want to go over that again, but there's an algorithm called Filterback Projection. You can actually do this. But my point is really just to say that, the point here that I want to make is that the fact that I collected this one line, or at least half a line in a Fourier transform, it's kind of like performing a projection. And if I would have been able to collect, let's say, also another line and another line and another line and another line, all of these are also projections. So I can leverage the same mathematics as I have in CT to compute the volume from its projections. So I have enough information to do that. Okay, that's kind of like the idea. Now, here's actually a screenshot of our scanner, and I've put a ball phantom. This is a phantom, that's the object. It's a ball that I put inside the scanner. And then what I did is I collected the free induction decay, right? Like the signal that comes out. You can kind of see that the signal that comes out is kind of like half a jink. You see? It starts here and it's kind of like, it's half a jink. So similar to what I just described before. And then if I compute the Fourier transform of this signal, this is the Fourier transform of this signal. What is it? It's kind of like a blurry half circle, right? Because the projection of a two-dimensional circle is really something like that. Okay, so that kind of makes sense. All right. Okay. So here's the idea of how to do what's called a projection reconstruction in MRI. What we're going to do is we're going to apply again an RF pulse while gradient in order to do selective activation. Okay. And here I color coded a few things. So what I'm going to do is the first time I'm going to excite, I'm going to apply the red sequence. So the red sequence applies a GX and GY will be 0. So that will traverse the frequency domain along this red trajectory. I wait till everything recovers. Then I collect more data. And the next data that I collect, let's say the blue one, I'm going to apply gx to be 0. And then gy, I'm going to be positive. And so that will collect the data along the y-axis in the frequency domain. And then if I run the green sequence where I apply a negative gx and gy being 0, then that will traverse the frequency domain from here to here. Okay, so now you've seen that I've collected like half a circle in the frequency domain. So a full diameter is actually a projection, right? So if you remember, the Fourier transform of a diameter will give me a projection. So I could potentially collect these projections and then be able to perform what's called a back projection, the same mathematic as CT, in order to reconstruct the object. Okay. Now, each one of these are not exactly diameter, but maybe you can say, oh, this one plus this one is a diameter. And this one, well, I can also collect another one over here. And I can use this whole thing over here as a diameter, right? So then I could do that. All right. So this is a way that's called projection reconstruction in MR, and this is how Lauterberg described MRI as, by basically rotating the gradients. I mean, pretty much the gradients here are g times cosine theta n and g times sinus theta n. Okay, so every repetition, I'm just going to change the theta such that I get a different projection. Okay, so if theta equals 0, then I'm playing g in x and 0 in y. If theta is 90 degrees, I'm playing 0 in x and then 1 in g in y, right? So on and so forth. But here's a better idea. I mean, this is on like a radial grid. I have to deal with all this projection reconstruction, but I can actually do something else. What if I do the following thing? What if I excite a slice, but then what I'm going to do is I'm going to, the red sequence is exactly the same, right? Like the red sequence basically says, don't play anything in y, and then in gx apply this type of a gradient. So that would correspond to, again, the same thing as I had before, collecting this radial line, right? But what if before I do this, I apply a y gradient with a certain time? If I apply this, what would happen is that from this time point to this time point, I will travel in the two-dimensional Fourier transform of the object up to here. And then I'm going to apply what's called a readout, which will I then collect the data. So then I will collect the data during this time. And then I wait till everything relaxes, and then I apply a blue gradient, like a blue size gradient here, so a smaller one, that will travel up to here, and then I collect a line. That's the third one. The fourth one, I will apply a negative gradient in y, so I'll travel here, and then I'll collect this line. And then I go again and collect it. So now I have my data collected on a two-dimensional Cartesian grid as opposed to on a radial grid. This part over here takes me to where I want to start. This is called a phase encode. It encodes phase in the image. That's what it does. It encodes phase in the image. And this is the readout. This is what's called a frequency encode. So that is the top part where we actually collect the data. Here we don't collect data. Here we just prepare the magnetization such that we are effectively traveling in the frequency domain, but we're not collecting any data. There's no point in collecting it. And then we collect the line after that.
What would happen
So
if
this is
you,
called, yeah.
sorry to interrupt. What would happen if you left the phase encode on while the GX was being read out? I know that would be
Oh yeah.
wrong,
Okay.
but yeah.
So like this, right?
Yeah. Why isn't that done?
Okay. So let's do that. Yeah, let's do that. Let's see what it traces. So I'm gonna pick a color. Which color should I pick? I'll pick orange. Okay.
Okay.
All right. So first of all, you start with some y, right? Phase encode. So that would go from here, and it will travel up here, right? In the frequency domain, right? Now you're going to start this readout gradient. So that takes you to the right, right? It takes you to the right of k-space. But because the y gradient is on, you're still moving in the y direction. So that will then take you
Diagonal.
and collect this line.
Yeah. Okay.
Does that make sense?
So you would just
So
fill
then if you do that,
k-space diagonally? Would you fill k-space?
well, I mean, I don't know. It depends what you do, right? Like if you actually extend the second one also, then what you would do in the second one is you'll go up to here, and then you're gonna go and like collect this line, right?
Mm-hmm.
So it's kind of like gonna be like a fan-like acquisition. It's so weird. It's gonna look like
Oh,
that's what's gonna happen,
yeah.
which is probably not ideal. It's very non-uniform.
Right. Okay. Thanks.
Sure. But the idea here is that what you want to do is effectively where you are in the frequency domain is really the integral of your gradient, if you think about it. Like moving here, what is it? It's basically the integral, right? Like if this is on, then it's kind of like you integrate over that, so you're kind of moving in k-space. Okay. Effectively, we said is gamma over 2 pi, g x times t, right? But that is just a generalization. When g is constant, then this is true. This is the integral, right? When g is constant, then this is the integral. If g is not constant, then you actually need to integrate. Okay? We'll get to that. Okay, so now I have data that kind of like make these kind of like horizontal projection. This is called 2DFT or spin warp also. That's another name for it. And so what we do is we're encoding some phase in the y direction prior to doing a readout in the x direction. So this is called a phase encode, and this is called a readout. And that almost gives me a two-dimensional Fourier transform. Still, I have this like problem with half of the Fourier. Like I'm not fully collecting the Fourier, right? I'm only collecting half of it, but not full of it. Anyone has an idea how to collect the full Fourier?
Could you apply a negative X gradient while you apply the phase encode in Y?
Beautiful, beautiful. What if I do that? If I do that, then the trajectory that I'm going to traverse is I'm going to apply this plus a negative of this at the same time. So in that case, I'm going to move negative in X and positive in Y, right? So I'm going to go in this direction. And then my X will move me in this direction. And then the second time, I'm going to move this way. And then my X is going to have me read this way. And then the third time, I'm going to move in this direction, and then I'm going to read the whole line. And then after that, I'm going to move here, and then like that. And then the last one, like that. So that is a possibility. Just by adding the small lobe, now I've collected a two-dimensional Fourier transform on both sides. Okay, so that is kind of like the idea of encoding, and this is how we collect then the two-dimensional Fourier transform. And once we collected this two-dimensional Fourier transform, then we can reconstruct it, let's say, by computing a 2D, like a DFT or, something like that. And we'll get to that later of what does it mean in terms of the field of view, remember, like the sampling and so on and so forth. Just a little bit more information that I want to add. So if you want to spatially localize information, we do that by applying gradients, right? The gradients allows us to spatially localize the contribution of spins by having them resonate at different frequencies that vary all the time. So that translates into a Fourier transform, and that allows you to be able to create an image. But there's other ways that people have done spatial localization. One that people have done, which is not very common, is B0 localization. What they've done is they created a very non-homogeneous B0, except, let's say if you have a volume, and you create a very non-homogeneous B0, except, let's say it's very homogeneous across a very small piece of volume. And so the signal that you're going to get only will come in from that volume. And then what you could do is you can apply gradient fields in order to move this kind of like uniform field into other places with electromagnets that you apply. And then this is kind of like almost line scanning. Okay, so if you move a uniform field throughout the volume, then whenever it's non-uniform, you're not going to get a contribution. But then where it's uniform, you're going to get a contribution of signal. So this is actually how Demodulation actually described imaging in the first place. It never really caught up because it's really not an efficient way of doing things. That was actually one of the arguments of him not getting the Nobel Prize, because his approach in imaging was something that never led to anything practical. Another one is RF localization. So for example, if this is a head coil or head array, like a head, you can put like a coil that's like really big that is sensitive to the entire volume, but you can also put, an array of small coils. And each of these small coils actually is sensitive to the RF energy that is emitted from the tissue next to it. And you can use that actually to locally receive signal. So for example, if I made a tiny, tiny coil and I put it on my skin and I create an image, then I will only get a signal from like the part of the skin that's close to the coil, but that's it. So that's another way of localizing information, is using local coils.
Hey, Mickey.
Now, as it turns out,
Hey, Mickey, on the top of the head, a small coil would be perpendicular to Z. Would it be worth putting one there?
Yes, but get it.
Okay.
It does, but it's again, there's a subtlety there.
Okay.
Yeah, I'll get to that when it makes sense. Now, if you think about it, local coils can give you some selectivity. Gradients give you selectivity, but maybe you can combine RF localization plus gradients together. And this topic is called parallel imaging, which allows you to speed up MRI acquisition significantly. And that's is an advanced topic that we're going to talk kind of more later in the class, how you can actually leverage the fact that you're imaging with local coils as well as gradients in order to actually go beyond the Nyquist criteria, the typical Nyquist criteria, and then let's say collect data at a spacing that is much larger than 1 over the field of view, which traditionally will give you aliasing, but because you're using many local channels, you're able to actually solve the problem. Okay, so we'll get to that. Another thing that you could do is what's called local excitation. So yeah, slice selectivity will give you a slice, but you still need to encode it in extra 2 dimensions. But it's actually possible to excite a box, like a tiny box. For example, there's a sequence called press, which is a single voxel sequence, which excites a single voxel. And then that's it. You only need to read out the signal from that voxel. But then you have to move it and acquire, so you're kind of acquiring 1 voxel at a time. It's very time consuming, but it's also not efficient from a signal to noise ratio point of view, and we'll talk about why a little bit later. Finally, we talked about linear gradients, but people have looked at actually leveraging nonlinear gradients, gradients that vary non-linearly in space in order to perform imaging. And that's another strategies that people have been using more recently. Okay, and maybe this could be a project if somebody's interested in doing a review or simulation of nonlinear gradients. That could be a really interesting topic for the project. Do I want to talk about that? Sure, why not? Okay, so here's kind of like a difficult situation. I told you that MR images are complex, right? Complex valued. I told you that, right? And you believe me, right? The thing is, there's no such physical thing as complex value, right? Like there's just no physical. There's nothing physical about complex value signals. And in fact, RF, I mean, it's just real. An electromagnetic field is a real field. Like it's not complex. There's just nothing about that, right? So so the question is, how do we actually get complex data? So the signal that we get is actually real. Okay, the signal that we receive from MRI, from the coil, is real valued, right? It's just real valued. And because it's real valued, its spectrum is conjugate symmetric. So if I have a signal around, coming from an MR system, let's say 1.5T, the signal that I'm going to get when I apply a gradient is going to have a certain bandwidth around 64 megahertz. And because the signal is real, it's going to have also its conjugate symmetry, a symmetric signal at minus 64 megahertz. Okay? This is just a fact. Now, the thing is, I really don't care about this entire bandwidth because my signal is very narrow banded. It is only located in a small band around 64 megahertz. And the thing is that this part is conjugate symmetric to this part, right? So really all my information is just represented in one of those bands, right? My information is just represented with this part of the spectrum. Because if I know this part of the spectrum, I know this part of the spectrum. It's just conjugate symmetric. Okay. So really, what I want to do is I want to be able to process that signal such that my result would just represent this part of the bandwidth. Okay? So how do I do that? Well, what I do is the first thing that you do is you perform demodulation. So you take your signal and then you modulate it by e to the minus 2 pi f0t. If you modulate this, then that will shift the spectrum to the left. Okay, so if I apply that, this is what I'm going to get. Then what I'm going to do is I'm going to apply a low-pass filter, which is going to throw out this part, and I'm going to end up with just this part. And then now I have a certain bandwidth, and the bandwidth now is very narrow, right? It's just the bandwidth of MR. It's not 64 megahertz, it's in the kilohertz ranges, right? So now I'm going to sample that, and yeah, I'm going to sample this pretty much bandwidth. Now, if you stare at this, you can kind of see now, wait, this signal is not conjugate symmetric around 0, so it has to be complex. Where does complex come from? Well, I did multiply by a complex valued number here. I modulated by a complex value number. Okay, this is how I got this. But hold on, is that even realizable? Is there a hardware that can implement something like this? Is there something that, in hardware that you can implement that will do that? Well, what is this composed out of? What is e to the minus I2 pi? Remember, what is it? It's cosine 2 pi f0t plus j sine minus 2 pi f0t, right? So effectively, I can implement the whole thing physically in hardware doing this. I have a source that produces frequency, and I multiply that frequency on one branch by cosine, and then the other branch, I delay it by 90 degrees, and then multiply effectively by a sine. So here I take the RF that comes in, and I multiply by cosine, and I multiply by sine. Okay? Then I perform low-pass filtering, then analog to digital converter, and then I'm going to call the signal that comes from here the in-phase signal, or I, and then the signal that comes from here I'm going to call the quadrature, or the Q, and then I'm going to multiply the Q by a complex number I, and then the in-phase add to it, and then I would get effectively complex samples. So this is physically, so this is all digital over here, so I can do whatever I want, right? So here's what happens. When I multiply by cosine, what is going to happen is I'm going to get two replicas, one replica that way and the other replica this way. So I'm going to get kind of an overlap of the, I guess, the positive part and the negative part at the center, right? So they overlap. Then I'm going to low pass filter. So these high frequencies are going to go away. Now I have a narrow bandwidth, and I'm going to then sample this. Hold on. Yeah. So now I'm going to sample this. This is conjugate symmetric, right? So the samples that I get are real, right? The samples over here are real valued. Do you agree? I multiply by a cosine, I low pass filtered, compute an ADC, so samples I get here are real valued. Okay. Now what I'm going to do is I multiply it with a sine. When I multiply with a sine, what would happen is that sine kind of flips one of those, and then, you know, the modulation is going to look like that. So this negative that, because a sine has a negative, like has a conjugate symmetry as opposed to a symmetry. So at the baseband, I'm going to get now the subtraction of these two. So when I perform a low pass filter, now I'm going to get the subtraction of these two. So then I can do ADC. Now this again, this is real signal, it's real signal. But now I'm going to multiply this by minus I, because now it's digital. Digital, I can do whatever I want on a computer. So a good way to represent it, the quadrature component, I'm going to multiply by an I, and then the other one I'm going to compute as the real part, and effectively represent these as complex valued. Okay, so what I've done using this apparatus is the same thing as effectively demodulating by e to the minus I 2 pi of 0, and then low pass filter, and then analog to digital converter of complex valued. But effectively, this can only be implemented this way. Okay. Now, there's another way of getting to the same math, and I don't want to go too much into it, but just go through maybe this process. If my signal is AT cosine omega 0t plus some phase that's changing over time, you can actually decompose this using trigonometry into some component with a cosine of phi of t multiplied by this cosine omega 0t. And then another component that multiplied by sine phi of t with sine of omega 0t. And this we call the in-phase component. This we call the quadrature component. And just for convenience, what we effectively then do is represent this signal as its analytical signal, which is this, and then our baseband signal is just the demodulated part, which is AT e to the minus phi t, which is really the in phase plus the IQ component. Okay, so if you want to go into more details of how we got this, you can go over that, and also it's in the book. But the idea here is really the fact that if my spectrum here about 64 megahertz is non-symmetric, then if I demodulate this and sample around 0, then because it's not going to be symmetric, then I have to represent it using complex valued. Now, this is a very common way of actually doing stuff in radio communication. This is done as well. So it's a very typical way of dealing with things by doing what's called an IQ demodulation, and then you end up with a complex signal representing a piece of the spectrum. Okay, any questions?
I have a question about slice encoding.
Okay.
When we're doing slice encoding, we are, as I understood, we are not changing the gradient itself, right? We are changing the center frequency of the RF signal. Is that what we are doing?
Well, I mean, yeah, the gradient center doesn't change, right? So you apply gradient, and that creates frequency versus space. And then you can decide where you want to center your slice if you modulate it.
Okay. And are we doing that by changing the frequency of the RF signal we are applying?
Yes,
okay.
Absolutely. The center frequency of the RF. Yes, this is how we do it.
Okay, thank you.
So effectively, the quadrature phase sensitive detection is we take our signal, we multiply by cosine and sine, we do a low pass filter. The result of the cosine is the in-phase component. The result of the sine is the quadrature component. And then the signal that we get is I of t plus capital I of t, the in-phase plus I, which is square root of -1 times the quadrature component. Now, when we think of the I component, we can also think of it as the mx of component of the magnetization in the rotating frame. And the quadrature component, we can think of the my component of the magnetization in the rotating frame. And we'll get to this, because the only difference between them is pretty much phase, right? Like if we have some signal and we multiply it by some phase, then you can shift. Let's say I have yeah, the only difference between the I and Q components are 90-degree phase, right? That's in the complex plane. So if I have then a magnetization that is just in the X direction, I can just represent it as, you know, its signal is going to be I of t. If I have a magnetization in the, you know, imaginary component, its signal is going to be Q of t. And then if I have anywhere magnetization that is pointing in some arbitrary direction, is going to be a combination of those, and it results in a complex valued signal. So it's a very natural thing to think of the phase of the magnetization. The phase of the signal represents also the phase of the magnetization, which is really where the magnetization is in the transverse plane. Hopefully, you know, while in class, you'll be able to get that more. Thinking about phase is a little bit elusive, but hopefully we'll be able to kind of get you to kind of appreciate and realize this as we continue on. Okay, so now we're finished with chapter 3. And so next lecture, we're going to start covering chapter 4, which is physics. And what we're going to do in chapter 4 is we're going to pretty much derive the block equation, which is a linear dynamic system that describes the dynamics of spins of the magnetization when you apply different magnetic fields on it. When you apply gradient fields, when you apply Rf fields, and when you apply a B0 field. We're going to derive that. And then after we derive this, and also for the case of relaxation, what happens in relaxation. And after we derive this, we're going to solve this block equation for excitation, and we're going to solve the block equation for reception, which would lead to this Fourier relationship again. So we're going to see it in you know, several different ways, so you can have slightly different perspectives on how people think about those things. Okay. So just the homework wise, please read chapter 4 before tomorrow, before Thursday. If that's, oh wait, or is it Thursday today?
Yeah.
Oh, so just next week we're going to talk about it.
Yeah.
Oh boy. Well, Professor Tamir is way ahead of us. Yeah. UT Austin is like 3 lectures ahead for some reason. I don't know. Do you feel I'm going too slow or I'm going at a good pace? I just let me know what's your thoughts. Just give me a thumbs up if it's a good pace. Okay. Yeah, my aim really is not to water hose you with, like, you know, a lot of material that, you know, kind of like, you know, will skip your basically not stay. And we'll get to where we get in this class. And my hope is that I'm going to actually teach another class next year, which is going to be advanced Paul sequences as well as advanced image reconstruction. So that's kind of like my hope. So if we don't cover everything, don't worry about it. You'll have that opportunity. And for that, I'm going to pay heavily by teaching EE16A in the fall. So, yeah. All right. So that's kind of my choice. All right. So have a nice weekend, and see you all on. I have office hours on Tuesday morning, so feel free to pop into my office hours. Okay.
Can you post these slides? Can you post the lecture slides?
Yeah, absolutely.
Thank
I will.
you.
All right. Take care, everyone.